Okay, I think we can start right now. Okay, so good day. So our word. So welcome to the Gaia STEM lecture series. Okay, so my name is Chia-Hui Chang. So so I would just so the original host, Dr. Shiru Lin, she's in a trip, so she's traveling right now. So I have the pleasure to how do I say that? Just hosted a lecture for her and to enjoy the following lecture with you all together. Okay, so today's speaker is Dr. Zhang Shuo. Okay, so she just joined Michigan University this summer in the Department of Physics and Astronomy. Okay, so before that, she was in Bard University, Bard College. Okay, and she graduated from Columbia University and received her PhD degree in physics, and then serving as a postdoc in MIT and Boston. I think I just heard that. Okay, so today's topic is the history of monster black hole at the center of our galaxy. Okay, so let's welcome Professor Zhang to give us the lecture. Thank you.
Thanks to Professor Chia-Hui Zhang for the amazing introduction. So let me share my slides with you. Let's start from here. It's my great pleasure to join you today and to share with you my research interest and to tell you a story about the history of the monster black hole at the center of our own Milky Way galaxy. Now, before we jump right into our topic today, I want to use a couple of slides to introduce to you what kind of research I do and what types of tools I use in my daily research. Now, my research involves two main focuses. Firstly, I'm interested in the most peculiar and powerful objects in the universe, the supermassive black holes, those black holes with like millions to billions of solar masses. Now, I'm particularly interested in those monster black holes close to us, like within our own Milky Way galaxy and also in the nearby galaxies. Another of my research interest is where do those cosmic rays come from within our galaxies? So cosmic rays refer to the very energetic charged particles moving in relativistic speed. So they're very fast and very, very energetic. But this is a whole another story that is worth another lecture. Today, we are going to focus on our own supermassive black hole at the center of the Milky Way galaxy. Now, in order to understand like how this like supermassive black hole is doing, or other types of cosmic objects anywhere in our universe is doing, we need to rely on some powerful tools, either space telescopes or ground-based observatories. Now, we cannot rely on our bare eyes to try to understand them, right? Now, just to name a few space telescopes I use in my research. Now, for example, here I'm listing 3 X-ray space telescopes run by NASA or ESA. For example, the Chandra, that's the flagship X-ray space telescope of NASA. XM Newton, that has telescope here on the upper in the upper right picture, and that is built and run by ESA, as well as NuSTAR, one of my favorite space telescope, which I'm very lucky to join the mission from the launch of the NuSTAR telescope, and it's still like going on strong, going very well nowadays. So I can just write my proposals to submit to their review teams and to ask for observational data, like observing time. And then if they give me some time, then I can obtain data and point the telescope to those targets that I'm interested in. I'm also a member of the ground-based Event Horizon Telescope collaboration. maybe some of you who are interested in astronomy have heard about Event Horizon Telescope, or maybe the first ever direct image of a black hole obtained by the Event Horizon Telescope. Now, the name of this telescope, which is not a single telescope, but a global network of many different radio observatories spread around the globe, that the name of it actually tells what it is, right? It is like use like a lot of resources on the Earth, and with one single super important goal, that is to image a black hole down to its event horizon. So as you can see in this map, the Event Horizon Telescope is actually consists of ground-based radio telescope located in different continents, in Northern, Southern America, in Europe, and in the South Pole, to just name a few. Now, one of the major breakthrough in the recent years in the astronomy field is the direct image of a black hole. So the first ever like direct image of black hole was released in April 2019. Maybe some of you remember, like it's all over in the news. That is the direct image of a very nearby supermassive black hole in the center of M87 galaxy. And most recently, our collaboration also released a direct image of our own black hole at the center of Milky Way galaxy called Sagittarius A star. And that's also an amazing image. We're going to talk about that later. So just to sum up, I use both space-based and also ground-based observatories to study different types of cosmic objects. Okay, so let's talk about what I'm going to discuss today. So firstly, I'm going to give you some background in the center of the Milky Way galaxy. Why should we care about the center of our galaxy, right? What's interesting and unique about it? After that, we are going to talk about what Sagittarius star, our own supermassive black hole, it is doing right now, today, right? And if I have time, I'll also discuss what Sagittarius star used to do a couple of hundred years ago, even a couple of thousand, a millions years ago. And I'll just conclude my slides with a summary and outlook. So first thing first, why do we care about the center of our galaxy? What is unique about it? Now, first, I want to show you the spatial scale that we are talking about. And what do we mean by the center of the galaxy, where it is with respect to the location of our solar system? Now, what you are looking at right now is a top-down view of our Milky Way galaxy, which is a spiral galaxy, right? You can see the different spiral arms with some long names there, right? And our solar system is located in between two major spiral arms within the Milky Way galaxy. Now, the center of the Milky Way galaxy, or galactic center for short, is somewhere right in the middle, in the like yellowish region, which is roughly the geometrical center of the Milky Way, and is also the dynamical center of the Milky Way galaxy. And I hope you can see where our solar system is located, as pointed by one of the blue arrows, right? Our solar system is sort of like in the outer skirts of the Milky Way galaxy, at about 8,000 parsec from the center of the galaxy. So yes, we are talking about astronomical numbers right now. We are using the distance unit of parsec. Some distance units you are familiar with that we use every day, like meter, kilometer, is no longer good to describe astronomical distances. So astronomers use like light years or parsecs to describe very, very like large distances in between two locations.
Excuse me?
Yes.
Yeah. Would you be able to use the laser pointer to show on your screen which part you are pointing to?
Oh, yes.
Yeah, that would be better. Thank you.
Yeah, it's just I cannot see my own pointer. I will try to. I will try to use my pointer.
So are you using PowerPoint?
I'm using Keynote.
Oh, Keynote.
I'm not sure whether that caused the problem, but I will try my best. It's just I cannot really see clearly where my pointer is.
All right, thank you.
So yeah, back to our topic here. So if you are curious, like how 1 parsec is defined, here I have a plot for you in the lower left corner, like what 1 parsec means. So 1 parsec equals to 3.26 light years. Now, light years might be more straightforward. It is actually a unit of distance, meaning the distance light can travel within 1 year. And 1 parsec is like 3.26 of that. Now, so that means that our solar system is about, again, 8,000 parsec from the center of Milky Way, equivalent to about 26,000 light years from the center. Now, when we talk about what Sagittarius star in the galaxy center is doing today, now please keep in mind the photons, it actually takes all the photons to travel 26,000 years from the center to the Earth, or to the telescopes orbiting around the Earth. So when I talk about, okay, what we see Sagittarius doing today, it actually happened 26,000 years ago, all right? So doing astronomy is like just doing archaeology to try to tell the history of the universe. Now, this picture might looks familiar for some of you. It's actually how the Milky Way look like with bare eyes. Maybe some of you, if you've ever had the luxury to go camping and stay far away from the light pollutions in the city, now maybe you were able to take a look at the Milky Way with your bare eyes. And we just talk about, okay, there is a center, right, in our galaxy. Our galaxy is just like a puffy pancake. And if you want to look towards the center of the galaxy, it's actually a side view. It's not a top-down view, because we are within the galaxy. It's as if you are sitting inside a pancake and you try to look at the center of the pancake, right? So it's a side view, right? Looking at a pancake from the side. The center of a galaxy is actually supposed to be the brightest and the most luminous of the entire galaxy because of all the strong gravitational pull. There are so many stars and other types of objects there. However, I believe all of you would agree that, okay, it's not obvious where is the center, right? Within our using our bare eyes in the optical light. It seems to be blocked by some of these blackish stuff, right? It's like hiding the center of the galaxy from us in optical light. So what are these stuff that is blocking our view of the galactic center? Why can't we see it with our own eyes? It actually turns out that these blackish, diffuse stuff, they are dust. Now there are just so many dust distributed along the galactic plane, in between us, the Earth, and the center of those galaxies. And because of those dust, the optical light cannot really penetrate. Actually, the optical light, our human eyes are sensitive to, they are extincted by this dust by 30 orders of magnitude, making it practically impossible to observe galactic center at optical wavelengths. Again, that is the wavelength our eyes are sensitive to. Therefore, it's almost impossible to study galactic center with our bare eyes, obviously, but also with optical telescopes is also almost impossible. So how can we gain some knowledge from the galactic center? Don't forget that the optical wavelengths, or some folks call it visible wavelengths, is only a very tiny, very, very narrow band of the entire electromagnetic spectrum. That is basically just the entire spectrum with photons carrying different energies, or if you like, the waves with different wavelengths. Now, from the longest wavelength to the shortest wavelength or the highest energy, we have radio band, microwave band, infrared, visible or optical, roughly in the middle. And then a shorter, even shorter wavelength or higher energy, we have UV, ultraviolet, X-rays, and the highest energy photons in the universe that we know, they are called gamma rays. Okay, so among all these like different wavelengths, the ones that I circle using the red rectangulars, like radio, infrared, X-rays, and gamma rays, they are the good wavelengths where using which we can study galaxy center. So photons in those energy bands or wavelengths, they are able to penetrate the dust and just travel 26,000 light years and eventually reach the telescope here on the Earth. All right, so we are not able to see the galaxy center in optical wavelength, but how does the galaxy center look like in radio, infrared, X-ray, or gamma ray? And there are tremendous efforts in the astronomy community to observe the center of the galaxy. It's always one of the most interesting spot astronomers want to see. Almost every telescope, whichever telescope that is able to see through all this dust and the probe galaxy center, I would bet almost every one of them has observed the galaxy center. So let's see how the galaxy center look like. From the longest wavelength, radio band. So here's the image of the galaxy center. Horizontal direction is galactic plane. It's about 100 parsec by roughly 200 to 300 parsec, centered on the galactic center, where there is a supermassive black hole called Sagittarius star. This image is obtained by maybe one of the most famous ground-based radio observatory called Very Long Array, VLA, where you can see some very peculiar filamentary structures, molecular clouds, and supernova remnants, all sorts of cosmic objects in the galactic center. Now, if we move on to the next wavelength, infrared, like near infrared band, here's how the galactic center, roughly on the same spatial scale, how it looks like in near infrared. This image is obtained by the very famous Hubble telescope. Now, what you are looking at is actually many, many stars, cool stars. So because near infrared is very powerful in detecting stars, the living stars there, the active and living stars. Although it seems to be that there is some pattern there. However, every tiny, tiny little dot represents a star. Okay, now we have to speak optical because there's no way we can see the galaxy center. So we'll skip that and go to higher energy or even shorter wavelengths, the X-ray band, one of my favorite wavelengths. Now this is also a picture or image of the galaxy center obtained by the Chandra X-ray telescope. So you are no longer looking at living stars, but you are looking at stellar remnants, meaning after the star dies, that they continue to exist in some form, like black holes or neutron stars or white dwarfs. Now each tiny dot represents a particular stellar remnants. They could be black hole, they could be white dwarf, and it could be neutron star. Since it's my favorite wavelength, I want to show you another image or a map of the galactic center that is obtained by the NuSTAR High Energy X-ray telescope. So this image is made by my collaborators and I a decade ago, back in 2013. And into higher energy, you are going to see fewer sources because fewer sources are able to produce photons with such high energy, but still you can see very strong X-ray signals from somewhere surrounding Sagittarius star, the supermassive black holes, and also some very famous X-ray sources there. We also have even higher energy into gamma ray regime. Now, this image is actually obtained by a ground-based observatory, a TeV gamma ray observatory called HESS. Into gamma rays, we are looking at an even simpler image, as if there are only two sources, right, and something in between. The brightest source, this blob, is coinciding with our own supermassive black hole. So people are still arguing whether this is indeed from the supermassive black hole or from something else. There are a ton of mysteries about the galactic center. Okay, so let's just pause a moment before we move on and summarize what we have in the galactic center, why it is so unique, why it is so interesting. Now, even just within 1 parsec, 3.26 light years from the center of the galaxy, you have 10 million stars, right? Imagine how many stars you have if you zoom out a little bit. Besides 10 million stars, we have different types of stellar remnants in the form of black hole, neutron star, or white dwarfs. Maybe they are isolated, or maybe they are in a binary system, like paired with another source, another object. We also have some very peculiar and extended and diffuse sources, like the 3 images on the right. For example, supernova remnant. That's very magnificent phenomena. It's like the sort of remnant of magnificent explosion of a star. And we can sometimes also see a very peculiar object called pulsar wind nebula. That structure is created by a very fastly moving pulsar, a type of neutron star. Now, in between of these isolated sources, you can also see some extended and diffuse, very fuzzy features. They are actually hot gas in the center of the galaxy, and their temperature is about millions of degrees, so high that they can emit X-rays. And of course, our superstar, right in the middle, our own supermassive black hole called Sagittarius A star, or Sag star for short. Now, its mass is about 4 million times solar mass. It sounds like, wow, it's like a lot of mass. It's huge, right? But, in the supermassive black hole family, it's considered small. Okay. So now, just if we can summarize with one sentence, I would say the galactic center, or sometimes we call it galactic nuclei, is a very, very interesting laboratory that can provide us almost anything like an astrophysicist is interested in. Okay, so we will just zoom in furthermore, and let's maybe forget all other objects, though they are really fancy and worth studying. But let's focus on the most peculiar one, the supermassive black hole. I want to use one slide to maybe answer some of questions in your mind, like what is the supermassive black hole and why are they interesting? Now, like we maybe already talked about a little bit, if a black hole has a mass of a couple of million to a couple of billion solar mass, then we call these most massive black holes, we call them supermassive black holes, on contrary to stellar mass black holes. Now, they are considered one of the most massive and also most powerful objects in the universe. And they are known to exist in almost all the known massive galaxies. So why? Why do we care about them, right? They are there. That could be the only reason that we want to study it in my own mind. But if you want me to provide more reasons, I would say that is like a good laboratory for us to probe physics under extreme conditions, especially under extreme gravitational field, under very, very extreme gravitational pull. And we can use such an environment to test general relativity. We can even study gravitational wave physics. And it's also known that evolution of the supermassive black holes at the center of a galaxy is closely related to the evolution of the entire galaxy. So hopefully that's the reason that can convince you that supermassive black holes are worth pursuing. All right. So next, now in order to prepare you to understand what's coming next, I want to tell you like what kind of information we can extract from the data obtained by a telescope, especially an X-ray telescope. Now, the way we try to understand, like for example, a supermassive black hole using a telescope is that, okay, we point our telescope to the black hole and we will collect the photon from it, from that direction. Now, when the photon from a black hole hits onto your telescope, hits onto the detector of your telescope, now what do we actually get, right? Some information, an X-ray photon arriving at my telescope. What information it carries include when the photon arrives at the telescope, right? Where it hits onto the detector within the telescope, how much energy a photon carries, and maybe also polarization information as well. Now let's start with where the photon hits onto the telescope detector. Now from this information, we will be able to construct a sky image using some sort of like coordinate, galactic coordinates, or maybe other coordinates, so that we can, construct the image and we can clearly see, okay, where this source is, how this source look like, the so-called like morphology study. Now we are able to tell whether it's a point source or whether it's like extended, diffuse with some particular shape. Now, next, when a photon arrives at a detector, now using this information, now we can produce a scientific product called light curve. So it's nothing mysterious. A light curve is a plot or like a function of like a count rate, how many photons received per unit time with respect to time. So as you can imagine, you can tell, okay, how much photon I receive in this hour and how many photon I received in the next hour. It can tell us like whether this source is stable or does it have any variability? Is it becoming brighter or fainter, right? Now, next, a third type of information, like what energy, how much energy a photon, each individual photon carries. Using this information, we can produce another very important scientific product in X-ray astronomy, and that is called spectrum, and also in other wavelengths as well. The spectrum is very, very powerful tool. In many cases, if we are lucky, we can directly tell what is the physics behind it, what is the radiation mechanism. So what is the origin of those photons by fitting the spectrum to different types of models. Now, a spectrum means how many photons we received, like maybe per unit area, per unit time, as a function of energy. It basically tells us, okay, how many photons we received at, let's say like 1 hertz, how many photons we receive at 2 hertz and 3 hertz, different frequencies or energies. Now it can really tell us like maybe what physics is behind all these emissions we are detecting. Now, lastly, a fourth type of information a photon carries is the polarization. It can, in many cases, also tell us what physics is behind it. It's just made possible by very recently launched X-ray polarization telescopes. Okay, so that is how we use the photons obtained by an X-ray telescope to study a source of the interest. With those in mind, let me tell you a story of what Sagittarius Star is doing nowadays. And if I have time, I'm going to very briefly tell you what Sagittarius Star used to do a couple of 100 years ago. Okay, so the question is very simple. What is Sagittarius Star doing right now? It is the closest. The fact is that it is the closest supermassive black hole to us. Now, every galaxy, a massive galaxy, hosts one supermassive black hole in the middle. Now, of course, Sagittarius star, the one in the middle of Milky Way galaxy, is the closest one. So, coincident or not, it's also one of the least active supermassive black holes that is known to us. So, whatever it is doing, we are sitting in the front row to see, right? That makes the proximity to us, makes Sagittarius star the best laboratory for us to study inactive or low luminosity supermassive black holes. Now, some folks would say, yeah, maybe it's not coincidence. The fact that it's not super active, it's not doing too much, it's not eating the materials, surrounding materials like crazy, might be a reason why there's life in our galaxy. But that's, of course, an open question. Okay, so here is some technical details, but don't be afraid. I'm going to talk you through these plots. You don't need to care about the details. I'm just going to explain what you're looking at. So although Sagittarius star is very inactive, however, it does not mean it's boring. It actually demonstrates daily flaring events, which are like cosmic fireworks, as if it's put up some fireworks show every single day. What do we mean by flares from a black hole, right? How do we define that? So the two images on the left, hopefully my pointer is doing what I want, is the light curve in infrared band and also X-ray band. So the infrared light curve is in black, and the X-ray light curve is the blue ones. Now, for example, if you look at the X-ray light curve in blue, so the contrast or brightness of Sagittarius star is like, okay, like pretty stable, pretty low, but suddenly increase, meaning it suddenly brightens up to some higher level before it drops back down to a faint level. And it happens very quick, within 1 hour or even less. Now, obviously, the brightness of the black hole or the luminosity dramatically changes within a short time frame. Now, we call such an event a flare, all right? So Sagittarius star almost like demonstrates such like flare, like fireworks every day. And that puzzles the astronomers a lot ever since their discovery in 2001. So the two images on the left, on the right, shows you just how astronomers can collect data of these flares in different wavelengths, from radio all the way to high energy X-rays in different wavelengths. So those data points just refers to data or observations obtained in different wavelengths, and we can feed it with different physical models to try to tell which models is good, right? And that can tell us what physics that give rise to these flares. So what's really cool about these flares is that the shortest variability timescale, where you can see obvious changes in brightness, is very short as 100 seconds. So that corresponds to a very small spatial scale, meaning flares can only take place at only a few gravitational radii from the black hole. All right. So everybody wants to know what is going on there, so close to the black hole itself. Now, I hope I didn't bore you with those technical details. Hopefully, these are some eye candies and the images that shows you X-ray image of Sagittarius star during the flare on the left, and 15 minutes of image before the flare on the right. The darker the color, meaning the more photons we receive per unit time. So as you can see during the flare, now you can see this blackish blurb, right? Meaning we detect a lot more photons than usual during a flare, but before or after the flare, you can just see this orange blurb where there's no particular bright spot because there's no longer a flare. Now, so these flares, which happens at only a few gravitational radii from the black hole, they are considered the keys to infer the physical properties under very strong gravity, like, for example, what is the magnetic field strength at a few gravitational radii, or what is the electron density. Okay. So over the years, now especially within the last decade, from 2012 all the way to nowadays, there has been a lot of efforts trying to capture Sagittarius star flares in different wavelengths. And of course, ultimately, we want to answer the question how they are produced, right? What physics is responsible to a production of these flares? Now, especially Event Horizon Telescope and the Gravity Observatory are like driving such study, paired by all sorts of other telescopes working in different energy bands. Now, very recently, the Event Horizon Telescope released a direct image of Sagittarius star itself. A lot of people have been waiting for this result for a very long time. Now, this observation was done back in 2017, but it takes more than 300 astronomers around the globe many years to get this image, where you can see a sort of like a blurred photon ring surrounding the black hole in the middle, in the dark shadow. So us, the high energy astrophysicists or the X-ray astronomers, we will use the X-ray telescope to observe Sagittarius star at the same time, together with the Event Horizon Telescope. And we can tell them, hey, here is when we see Sagittarius star put on this firework, when they start to emit, to exhibit a flare, and when the flare stops, like the light curve I'm showing you. That's one example of flare we detected back in 2018. So this effort is still ongoing. Now, let me show you some most recent result of Sagittarius star flares obtained by a student in my group. So Rose Xu, she just graduated from Bard College just 2 months ago, and she's going to University of Cambridge to continue on her graduate study this fall. So for her senior thesis as an undergrad student, she was able to study the NuSTAR X-ray data, so data obtained by the X-ray telescope called NuSTAR from 2016 to 2022, and she was able to discover 7 new Sagittarius star X-ray flares. For example, the image on the upper left, this light curve you are looking at, is one light curve that Rose produced, where you can see a flare very clearly with some mysterious double peaks. And there are also other flares that she found. On top of that, she also found a very interesting trend by combining 14 flares. And she tries to see, is there some trend in between these flares? And she actually conclude that brighter flares seem to have slightly different spectra than the fainter flares. So we don't need to go to the details in the image shown in the lower right. We just need to know brighter flares and fainter flares could have different spectra, and maybe that point to potentially different origin. It's still under investigation, but it's a very interesting trend that she found. And so she was actually invited to present her findings in a press release conference organized by the American Astronomy Society a couple of months ago in January this year, and just talk to the press and also astronomers about these results. So that showcases how a young scientist in very early career stage as an undergraduate can do. So I want to use this opportunity to talk to the young audience here today. So firstly, thank you for coming to the talk today. And I really want to tell you that there are so many things out there in the universe waiting for you to explore. The sky is certainly not your limit. Even our galaxy is not your limit. There are a lot of amazing things beyond that in the universe. Now, another student work from my group that I want to show you, also produced by undergrad students, is discovery of something new that is unexpected. So it's a pleasant surprise to all of us when we look closer to the same large data set of Sagittarius star in hard X-ray or high energy X-ray, and we see this region at 1 parsec from Sagittarius star. We call it like a news source because we don't know what it is. It's this unexpected completely. We are trying to use different models to tell what this could be, but it's definitely there. It's real signal. So my students was able to fit the image very carefully with different types of models to try to understand this source. And this work is carried out by Ivan Tay and Ivy Lee. Both of them are used to be undergrad students at MIT. And right now, Ivan Tay stays at MIT. Ivy Lee is right now in PhD program at Rice University in another subfield of physics. But they did this amazing work. Okay, so I have a couple of minutes left. I'm hoping to wrap up within 5 minutes. I just use a couple slides to show you how we can infer what Sagittarius star was doing in the past. Now, in order to tell people, okay, so what was Sagittarius star doing 100 years ago, 500 years ago, or thousands of years ago, right? Of course, on top of 26,000 years. Now, we cannot point our telescope to Sagittarius star itself, but we need to zoom out to look at the surroundings of Sagittarius star, which can hopefully carry some footprints of past activities of Sagittarius star. Luckily, the galactic center is not in short of that. So this image shows about 200 parsecs from the center of the galaxy. And you can see a roughly a ring-like structure, right? Like a ring there. And they are actually molecular gas. So basically made of molecules, cold molecules. And this structure is called the central molecular zone. It contains about 5 to 10% of all the molecular gas of the entire Milky Way galaxy. Okay, so why do we want to look at the molecules in the galaxy? Because if there were ever some energetic X-ray photons from Sagittarius star, from the black hole, now those photons can hit into the molecules and got reflected or got scattered to the direction, into our direction, right? And then from this reflection, we are able to infer what Sagittarius star was doing a couple of hundred or even a couple of thousand years ago, because it takes some time for the light to travel. That's the a few hundred years is the time that takes a photon to travel from Sagittarius star to a nearby molecular cloud. So that's how we do this extra archaeology game to tell the history of Sagittarius star. Now, hopefully this cartoon can also help. So if there are some X-ray photons going from direction of Sagittarius star, eventually it hits onto a molecular cloud, and the X-ray photons will be scattered into different directions, including our direction, right? And we study these reflected X-ray photons, and in order to infer Sagittarius star's past history. Now, we don't need to go into the mathematical details. If you are interested, you can check out some old papers from our group and other groups. I think all we need to know today is that we can measure some observables, like the distance between molecular cloud and black hole, brightness, X-ray brightness of a molecular cloud and other stuff. And we can infer, okay, how bright Sagittarius star used to be a few hundred years ago. Now, thanks to a lot of efforts from different research groups, so this image on the upper left can very well summarize Sagittarius activity history. So the red star here mark Sagittarius activity nowadays, where it's very quiet, it's very inactive. Now the horizontal axis is the time going to the past. Vertical axis is luminosity or brightness. If you go back to a few hundred years ago, right, as those purple star shows, Sagittarius used to be much brighter, much more active just a few hundred years ago. If you go to a few thousand years or tens of thousand years, it is even more active and even more luminous. Now, if you go further back to a few million years ago, some other phenomena, astronomy findings suggest that Sagittarius could be in its like most active or brightest stage. So it seems to be in a stage where Sagittarius is like dimming down, like become like a less and less active over the past few million years. But that's one possibility. There are also other scenarios. This is a very, very interesting trend, like astronomers want to prove or gain more evidence to support. So lastly, I promise we are almost done. Just want to showcase some other works like falling into this category, like two of my students or collaborators, Field Rogers, who graduated from MIT and is right now a postdoc at UC Berkeley, and Natalie Jones, who graduated from Bard and is right now at Northwestern University pursuing her astronomy PhD degree. So two of them, they studied different molecular clouds, SAGI-V2 and the SAGI complex, and they were able to constrain Sagittarius brightness 100 years ago using one molecular cloud, and Sagittarius brightness 400 years ago using another molecular cloud. And they reached some sort of like consistent conclusion that Sagittarius indeed used to be a lot brighter and active a few hundred years ago compared to nowadays. What caused that is largely a mystery. I'm hoping to answer that question in the future. So lastly, I'm going to just summarize what we talked about today. I think the same image I showed you a couple of slides ago can perfectly summarize it. Like Sagittarius, our own supermassive black hole, nowadays is very quiet and inactive, besides the very mysterious daily flares. However, if you zoom out and out, looking at its surroundings, it seems to suggest that it used to be a lot more active with enhanced activity a few hundred and thousand years ago, and even like a few millions years ago. And what's causing that decline in activity, we don't have a definite answer yet, but hopefully we can give you such answer in the next decade. I'm going to stop here and thank you for your attention.
Thank you for this wonderful talk. So I don't know the audience, but for me, with many 专有名词, so probably it's better that we understand them, because during the talk I have to look up the names and trying to, okay, so if they are translated in Chinese, then probably I understand more about it. Okay, all right. So let's welcome our young audience to ask questions if you have. And before asking your question, you can say your name and where you are from. So let's know some more about you. Okay, thank you. 那我们接下来就开放大家听众们来问问题。那对我来讲啊，那个就请同学就是在讲 问问题的时候也说一下自己的名字，然后你是来自什么地方哈，然后比方说你是几年级的哈，那这样让大家知道一下。OK， 好，那我们就开放同学们来问问题好吗？好，然后我们让同学想一下，那对，这里面有在你演讲的过程中有2个问题，然后其中有一个是在问，应该是数字，就是说您在讲那个有多少个光年，然后从 galaxy 到我们的太阳，从 galaxy 中心到我们的太阳的这个部分。那我试着去回答一下，但是我不确定这个答案是不是对的，就是您说是有8kpc。所以意思是不是就是8000乘上3.26光年？
对的，是这样的，就是8000个parsec，然后1个 parsec 是3.26光年，所以就是把8000乘以3.26就是26000光年，就是我们的地球或者是太阳系到银河系中心的距离。
是啊，那这个是原本这个地方的一个留言板上面的一个问题。那还有另外一个问题，他是在问说，好像原本我们观测有很多年，好像2016年刚好是漏掉了。刚刚有一个同学在问这个问题。
这个这个同学观察的非常的细致，
观察细致，
在这张图上面。是的，就是2016年，好像我记得是那个年的观测的数据可能不是非常的多，但是是有的，确实是把它漏掉了。我后面会把它加上，谢谢这位同学。
好，谢谢。好，那我们看看同学，你可以举手发问。
也欢迎同学们，什么问题都可以的。
对，或者你开了麦克风，我们其实就大家都很客气。对，
就是不管你有什么问题是关于今天我们讨论的这个科学的问题啊，或者是甚至是一些关于就是 career 的问题啊，我自己的这个研究的经历的问题都可以的。
好，那我先来问个问题好了，就是您前面提到就是说您参加了好几个科学工作团啊，包括像那个什么 Event Horizon Telescope 这一个，或者是像这个 New Star 的这一个工作团队等等，就是好几个工作团队哈。那您当初是如何加入这些团队的呢？
我觉得张老师问了一个非常好的问题，可能很多年轻的同学们也很感兴趣，就是说怎么能加入一个大的一个科学的团队？因为如果你加入到一个很新的或者是很大的科学团队，那可能你会有一个很好的平台来做你想做的科学。这个有的时候可能确实是有一些是运气的成分，这个是不得不承认。然后有的时候也是可能你的目标如果非常明确，如果你真的知道你想做什么，然后你可以去主动的出击，主动的去联系这个就是做这个方面的科学家和教授。比如说可以和同学们分享一个例子是，比如说我在申请graduate school 的时候呢，比如说我当时会知道我想做的是，就像我刚才说 high energy astrophysics，就是高能天体物理，然后我知道我想做黑洞，可能我不知道很明确的，但是这2点我很清楚，就是我想做 X-ray X 射线，天文，然后我想研究黑洞，什么质量的都可以，什么距离的都可以。然后我就会关注一下，最新的，比如说 NASA 啊或者 ESA 有什么样的望远镜，有什么样的科学组，是能有一个新的望远镜。能有一个新的望远镜，他们的目的就是研究黑洞。那这样我就可能看到了，就是像我刚才给大家展示的这个望远镜 New Star，所以我当时因为是2010年开始 graduate school，而 New Star 呢，当时正是在筹建的过程中，它是2012年发射的。那我2010年去加入的话，这是对我来说，对一个 graduate student 来说是非常非常好的一个机会。我可以了解到这个望远镜是怎么甚至是怎么搭的，我能参加到在它发射之前，怎么来做这个光学设备，这个是在我当时在Columbia University 的这组里面，来做的一个事情。然后我能了解到，就是说怎么来搭光学的部分，然后这个探测器是怎么做的，那是在加州理工做的。然后一直到它2012年发射，那我可以看到它发射，然后发射了以后呢，它就开始收集数据。然后观测银河系中心啊，观测 Sagittarius Star 这个超大质量黑洞， 然后这样我逐渐的转向data analysis，就是分析这些数据，然后也能做我想做的科学。所以说，如果你知道你想做什么，你可以就是去主动的出击，很多老师也都会非常愿意。如果你有一个明确的科学的目标，如果没有的话，也完全没有关系。那可能会有一些随机的成分和运气的成分，但是只要你去了一个大概比较好的团队，那可能很大概率你可能会有机会，让别的人会告诉你，会推荐你进入一些不同的科学组。
是，谢谢。好，我们这边有线上也有几个问题哈。那我们是不是请林子轩同学，您要自己来问吗？因为我看你打了字了，你要不要来举手讲一下？
想问说，之前有听说过黑洞可以靠重力波来发现黑洞，那想请问还有什么其他的方法吗？因为我刚才有一些地方没听到，抱歉，如果有说过的话。
谢谢你的问题，这是个非常好的问题。所以这可能这个问题我觉得是和就是我们天文最新的这个天文领域吧，最新的这个很火热的这个 topic 就是叫 multi-messenger，就是多信使天文。就说，我们怎么能去了解一个非常远处的物体，离我们那么远，对吧？很多很多光年以外。那传统的天文学其实就是研究光子，photon，就是我们说这个刚才说 X-ray band、gamma ray，然后 radio 啊，然后 infrared optical，这些都是光子，只不过是不同能量的、不同波段的光子，但它们都是光子。传统的天文学就是靠用望远镜来捕捉这些光子，来研究这些黑洞或者是其他任何远处的物体。但是你刚才提到了，我们可以用引力波，对吧？gravitational wave 来了解黑洞，尤其是如果有两个黑洞，它们就是互相绕着转，spiral around each other，那这是一个很好的一个就是非常完美的一个引力波系统，它就会释放引力波，一直到它们如果在这个 collide 了，就是碰撞，然后变成一个更大的黑洞，那这个过程中又会释放很多能量，然后释放很多很多的就是能量是用引力波的形式释放，所以引力波肯定是现在也是非常的火热，很多的科学家在用引力波来研究黑洞啊，然后以后会用引力波来研究超大质量黑洞，也会用引力波来研究中子星，甚至是白矮星 （white dwarf） 都是可以的。这是另外一种手段，就是完全和我们传统的天文学就是不太一样的一个手段。另外一个多信使就是用中微子，但是就是有一些超大质量黑洞也有可能会产生中微子，中微子也是不同于光子，也不同于引力波，是另一种信使，它也可以带着黑洞的信息，然后到达地球。我们可以用研究这些中微子一种基本粒子来了解黑洞在做什么。
谢谢老师。
谢谢。那我们接下来还有一位周岩同学，周岩同学，您可以开麦克风来发问吗 ？OK， 他好像没有开到麦克风。那我帮他把这个问题，他是有提到说刚刚您演讲提到，说研究光的 polarization，那他要问说这种 polarization 不同的时候，它代表什么样子的意义？会有什么不一样吗？
这是个很好的问题。对，我们知道就是polarization，它是就是如果你有一些光子，不管是 X-ray 波段呢，还是 optical 波段，它都会有这个polarization 的这个偏振的信息。它有可能是就是 linear 线偏振，也有可能 circular 或者 elliptical 就是圆偏振。可能应该是这样翻译的。然后如果是不同形式的偏振呢，它可以告诉我们就是可能有不同的物理的模型，不同的这个辐射机制 radiation mechanism，就它有可能是比如说 synchrotron 啊，有可能是康普顿散射啊，或者是有可能是其他的同步辐射呀，就不同的这个辐射的模型，然后通过 polarization 偏振可能会告诉我们。另外 polarization 这个偏振有的时候有一个角度的问题， 然后用这个角度的信息，那也能有的时候能告诉我们，甚至关于就是两个不同的object，就是两个不同的物体，它们之间的距离是多少，或者其中一个物体距离就是另外一个的它的一个角度啊，或者距离，这个信息也能从偏振角得到。
是，所以是不是说像这样子的一些资讯，其实它也是我们要去发掘说它跟某一些现象之间的关联，然后看看说这些讯息可以用来，感觉上也就是做资料大数据的分析，是不是？
是这样的，尤其就是像这一张那个 PPT slide 上显示的，其实就是每一个小的部分，给我们一类的信息，但是我们要就是收集尽可能多的信息，然后综合起来，然后最后的目标反正就是理解这个物理过程是什么，对吧？然后我们看到的这个东西到底是什么？第一个我们要回答这是什么？我看到的东西是什么？它是什么东西在产生 X 射线？它是一个黑洞啊，还是一个其他的中子星啊，或者其他什么？然后另外一个就是它到底在做什么？就是什么物理模型可以解释我们看到的东西？那为了回答这两个非常重要的问题，我们就要去看它的光谱啊 spectrum， 看它的光变曲线 light curve， 看它的偏振 polarization， 看它的图像这个 image 或者 morphology。然后这还是一个波段，那其他波段我们也要做同样的事情，看另一个波段它的图像，然后光谱和这个光变曲线，综合所有的信息，最后你可以去用不同的模型，非常非常复杂的模型来试图解释你看到的这些数据，然后最后甚至你可以动用更加厉害的手段，比如说非常好的一些计算机模拟系统，同时可以解释所有这些事情。如果它能解释，那它就是一个好的模型；如果它能解释这个，并且它能预言其他的，那它就是一个好的物理模型。它可能就是一个正确的一个物理的模型，甚至可以填到教科书里面的一个好的解释。
是，好，那我们最后这边还有一个问题，来自黄子彤。那不晓得黄子彤方不方便打开麦克风来问这个问题呢？
老师好，我是黄子彤，就是我想要问一下，超大质量黑洞会移动或者改变方位吗？
哦，这是个非常有趣的问题，谢谢你这个问题。就是说它应该说在至少在我们人类的这个生命的这个长度上呢，我们不会看到什么显著的变化。如果说一个超大质量黑洞它的位置啊或者速度有什么变化，那还是在比较长的时间的尺度上会发生的。但是就如果说它是一个它没有一个就是它在一个怎么说，一个独立的一个星系里面吧，然后它周围没有另外一个星系，它们两个绕着转呢，那它可能相对来说它的改变会慢一些。但是呢，有一些天文学家他们也观测到这样的系统，就是两个超大质量黑洞分别在两个不同的星系里面，然后这两个星系连同着这两个超大质量黑洞，它们会绕着彼此转，叫这种就是 dual supermassive black hole。然后这样的话呢，他们可能在非常漫长的时间的尺度里面，最后他们会越来越近，然后互相绕着转，越来越近，最后甚至可能就是合并成一个星系，然后中间有一个黑洞。那这样你也可以想见，在漫长的时间尺度上，那这两个超大质量黑洞它们的位置和速度都会一直发生变化，一直到最后，甚至两个都消失了，然后合并成了一个更大的黑洞。所以这可能是一个比较极端的例子来解释，对的，这个超大质量黑洞的位置和速度是都可以改变的。
是，谢谢张老师的回答。刚刚应该留给那个子彤来，谢谢。好，那
谢谢老师。
是好，我心里面在想说，我们以前小时候接触到天文的部分，好像就是看到他拍的那种很漂亮的那个银河啦，或者是太空的照片那样子。那我自己在做 computer 方面的东西，不过我自己本身也不是做影像分析，但是 计算机科学里面的话，他们有对大量的这个做影像的分析的。那当然就是大部分是我们现实社会我们日常生活的这些照片。但是我心里面在想说，这些望远镜他们拍出来的照片，是不是说很多其实大家都是一样的照片，但是就有一些就是很特别，就是像你给我们看到那种好像很漂亮的颜色，然后就是它形成的某一种跟就是可能在众多里面它就是很不一样的东西。那我们就是来分析说，哎，这些东西到底是什么？那像刚刚提到，就是说，我其实也蛮好奇的，就是像我们这样子拍照的时候，它能够确定说，哎，这个光是来自那个地方，像是这人马座的这个say 就是 A star 这个位置吗？还是说它可能是从不同地方所呃好照射过来的？这其实是我还蛮好奇的。
哦，谢谢这个问题，这是我觉得是一个特别特别经典的，然后在天文里的问题，就是说，如果我比如说在这一页这张图里面，就是如果我看到这些，哦，我知道有 X-ray 这个 X 射线光子从这个方向过来，对吧？然后因为我知道我把这个望远镜对准了那个角度，所以我知道这肯定是银河系中心，然后几个这个 parsec 以里，然后但是我觉得这个问题可能是说，那我看到这些 X 射线光子从这个方向过来。那它到底是不是从，这个黑洞的位置呢？还是有可能是从比如说它后面有一个圆，这个距离是什么？是这个意思吗？或者是它周边同样的
对，
距离？
我一开始是想到说是有没有可能是周边来的？那你刚刚讲的另外一个是说有没有可能是它更后面的？
对的，就这两个，我们怎么来区别呢？首先这两个问题是有没有可能周边呢？那这就是取决于你的望远镜它的分辨率有多好，它的空间分辨率有多好。如果它的分辨率足够好，那我就可能知道说它大概率是来自于比如说这个黑洞，而不可能是它比如说1个 parsec 或者是10个 parsec 以外的。比如说我的角分辨率要是空间分辨率要是1个 parsec，那我就能确定说，那至少是来自于它1个 parsec 以内的。如果我的角分辨率更好，那我就能看到更细节，我能更确定它就是来自于黑洞本身。那另外一个问题，它有没有可能来自更远处？这个是个就是我觉得很经典的问题，就是很多人我最开始学天文我也会问，那我看到它，我怎么知道它是来自于银河系中心黑洞，而不是它后面的刚好是在同一方向的东西呢？就是这个宇宙虽然它有很多的东西在里面，但实际上宇宙是非常空旷的。就是我们可以去做一个就是一个快的就是计算吧，但是在这里我不会做了。就是说你如果看到一个物体，它来自于光子来自这个方向，那它可能说99%的概率它是来自于这个圆，而不是在同一个方向的更远处圆。就你看同一个方向，更大最大的可能，甚至可能90%、99%以上，只有一个物体。
了解。
宇宙很大，但其实它有很多东西，但实际上它蛮空旷。
是，谢谢这个回答我的这个疑问哈。那我们下面还有一位雷凯杰同学，那雷同学你可以先开麦克风，然后你可以说一下你的来自什么地方。
然后我在台北，然后对，我叫雷凯斯。然后我刚才有提到说black telescope 来 capture black hole 是通過 photons 光子，那它可以通过 electromagnetic wave 来 capture 吗？因为我也不太是 like how light travels in the universe, like does it travel in wave or photons?
对，这是也是一个很好的问题。我想你这个是，这个问题可以用，波粒二象性来回答。就是说，我们是看到了这个光子 photon，但是呢，就是后面你可能会，如果有兴趣的话，你可能会接触到 quantum mechanics，就是量子力学。那里面讲了，其实，是光的本质到底是什么呢？就是它既是光子 photon，又是电磁波 magnetic electro wave。所以我们在所有的这些结果，它既是 photon 光子，又是 electromagnetic waves。 但是如果你到更高的能量的时候呢，它的粒子的特性就会光的粒子性会更显著。这是为什么我一直在说 photon，因为我主要是研究 X-ray 啊、X 线、gamma ray，在这么高的能量，光表现的性质更像一个粒子，就是 photon。但是如果你要问我的同事，他们是做 radio astronomy，就是射电天文学的，他们就不会说 photon，他们就会说 wave，他们就会说多少赫兹的 frequency 啊，然后波长是多少，因为在他们的这个everyday 的这个 research 里面，就是说他们研究的就是波，所以这是光的，就是波粒二象性。
OK，谢谢谢谢。
好，谢谢谢谢。好，那我们时间好像也差不多，那是不是我要问一下那个丽君。
是老师啊，是还有就是我刚刚有看到高老师有问问题，还是高老师方便问问题吗？因为你那的问题我不确定我能不能念出来。高老师是我们天文所的一位老师。
哦，是好，
就是在你的谢谢你的这个演讲啊，就是在你最后一个投影片上面哈，我就看到了哈，就是在几百年或者说1万年左右哈，那个大概是10个14方的这个2，或者说10个11次方的2，那这个是一个 tidal disruption event 吗？就是大概在这个能量范围吗？
我觉得对您这个问题非常好，这也是我们特别想回答的一个问题。就像我说的，就是我们现在的知道的，就是可能 morphology 上面来说，就是能推断出，比如说 Sagittarius 在几百年前，它可能有2到3个orders magnitude 量级的更亮，但是这个离它的这个爱丁顿亮度 Sagittarius 爱丁顿亮度还是很远的。它可能几百万年前，有可能能达到它的爱丁顿亮度。然后我觉得，如果是 tidal disruption event，它可能如果是一个完整的 tidal disruption event，它可能会要求 Sagittarius 到接近爱丁顿亮度，会非常非常的亮，而且持续很久。但是几百年前的这个是一个比较小的一个 outburst， 一个大的爆发。它持续的时间可能也未必有很久，可能是在几十年的尺度。那它这个原因到底是什么呢？可能未必是一个非常经典的 tidal disruption event， 可能会是一个比较小的 tidal disruption event， 比如说不是 disrupt 了一个 star， 可能是一个小的 asteroid 啊，然后一个很小的 planet， 甚至是molecular cloud， 就是分子云，这样的一个 event 有没有可能导致一个10年左右的小型爆发？我觉得这个也是比较有可能的。所以我觉得您说的这个解释，我觉得应该是很多人会同意的。
好，谢谢谢谢。
OK， 谢谢高老师。好，那那我想我们今天这个10点数，哇，还有我们多了15分钟。不过很谢谢那个演讲者，然后留这个时间，然后跟我们的听众互动，然后也谢谢各位听众的参与，然后这个林子轩、周岩、黄子彤，还有瑞克雷，还有高老师你们的问题，谢谢大家。那我们今天的这个盖亚科普讲座，我们就到这个地方结束。那欢迎你下个月来再参加我们下一场的那个科普讲座。谢谢大家，好，那我们下次再会，拜拜。
谢谢谢谢。
谢谢。